almost brainwashed into thinking that cavitation is evil, it's bad.
Yes.
Well, cavitation, cavitation tamed and harnessed to achieve metallurgical goals is something unheard of and alien to the metallurgical industry. So this is a typical case of where something has to be unlearned before new possibilities can be embraced. And this is because engineers are taught from school, university level. They taught about all of the different ways to design out cavitation from equipment, from pumps, from pipe ends, from mixers. And the reason they are taught to design it out is because the energy release of cavitation just destroys equipment. So a cavitating pump impeller, for example, it will take about 3 days for that impeller to be completely obliterated, and I'm talking like a strong metal impeller, and it could spin around there for days quite happily, for months, without cavitation. But if there's cavitation present, 3 days it's destroyed. The same thing with a pipe bend. If you get cavitation in a bend, give it 2 or 3 days, you can have a hole in that bend.
Wow.
And so engineers have sort of been indoctrinated, if I can use that word.
Okay.
They've been almost brainwashed into thinking that cavitation is evil, it's bad,
yes,
and it's like a swear word.
Get rid of it.
Get rid of cavitation.
Wow.
But if you just stop and right there and think for a moment, if there is that much force and power in this cavitation effect, what if we could use that energy? What if we could capture that, harness that energy, and apply it to the ore that we want to extract? To try and achieve some metallurgical good. And at Gold Ore, that's exactly what we did. When we set about designing the MACH reactor, we could have chosen many other sort of principles to base the reactor on. We could have made a sparger, easy to do. We could have created a static mixer or just another shear device. But we didn't want to do something that's been done before. So we wanted to break the mold.
Sure.
We want to be the first to do something.
Wow.
And that's why we chose cavitation as the basis of design for the MACH. And so the MACH has these hydrodynamic cavitating ventures where we accelerate pulp to over 30 meters per second, which is actually supersonic for bubbly flow systems. 20 meters per second is MACH speed for slurry systems. So if you're at 30, you're actually supersonic. So that's how fast the pulp's actually flowing through those materials. And we induce this cavitation effect. We generate those pico bubbles, which helps us for leaching. It also helps us to pick up those really, really fine, below 10 micron valuable mineral that's ordinarily would be just lost out to the tailings dams. We're able to collect that if we precondition effectively with the MACH reactor. So, it sounds all wonderful, but, we are dealing with extreme forces and extreme things. So we did quite a bit of development work around getting to the perfect geometry for those venturis so that, we're giving the high-speed slurry through there more or less the natural shape, the natural flow pattern that it's going to want anyway. That's how we shape the venturis.
Okay.
And that helps a lot to minimize the wear. And then it's been the materials of construction as well, which we've gone quite away with that. We've tried a lot of different things, and we know what material to use in which section of the reactor, and got it to a point where the lifespan now is well over 10 years. For a MACH reactor. It really is a piece of equipment that needs zero maintenance. By zero, I mean none, absolutely nothing. Maybe you will inspect it, but that's that. So it's zero hassle, and you're able to get maximum returns of it. So it's extreme, but it can give you extreme returns, extreme profits. And all I can say is sometimes, you've just got to have the courage. You've got to fight fire with fire.